In this video, we're going to talk about some of the fundamental principles of psychological science and science in general. But first, a bit of a non sequitur. I want you to think about what success looks like in terms of learning in a school context. And I have a question for you. It's a true or false question. Does the average student learn more or better in person compared to online? Do you think this is true or false? If you said false, you are correct. There is no statistically significant difference between in-person and online learning in terms of standardized measures like exam performance. Now, the broader question that I hope to answer here with all of you is, well, how do we know this exactly? And in order to answer that question, we have to talk about science. Our definitions of science include several key elements that we're going to discuss here, some of which are also highlighted in your textbook readings. This includes things like systemic observations, inductive reasoning, testable and verifiable predictions, and generalizable conclusions. Systemic observations means that we are careful when we're collecting data and we don't do it haphazardly. So we want to be careful, for example, when we're measuring and assessing our variables and running analyses. Inductive reasoning is mentioned in your textbook as one of the key elements of science, and this means that we draw conclusions based on our observations, and this specifically includes quantitative and qualitative data. Testable and verifiable predictions or hypotheses means that our ideas can be tested and evaluated based on the available materials and methods. We don't make claims based on faith or wishful thinking. And finally, generalizable conclusions means that the knowledge we get is not simply about the specific tools and the specific people that we studied, but that we can have knowledge that extends beyond that to other circumstances and other individuals. There's a nice example of inductive reasoning from your textbook that I want to share with you. So, for example, if you see this sequence, the star followed by the rectangle repeating itself a few times, and you're asked to predict what comes next, you'll probably pick the rectangle. But that's with only 5 shapes in the sequence. What if we had more information? What if we knew this? If we knew this, the 2 triangles coming after the third star, now we might make a different prediction. So if we're asked to predict what comes next in the last sequence, instead of picking the rectangle, we'd probably pick the triangle. And this shows the benefit of inductive reasoning. The more data and the better quality data we have, the more accurate our predictions become. And that is a key element of the scientific method. These are the 5 principles championed by Thomas Kuhn that are also covered in your textbook: accuracy, consistency, scope, simplicity, and fruitfulness. Accuracy simply refers to the idea that our explanations and theories should match the real-world observations we make. This is probably the most obvious part of good science. What we say is true has to actually be true. Then we have consistency, which means there are similar findings across different fields of research based on the same scientific ideas. The theory of evolution, for example, gives us ideas that yield consistent findings across different fields of biology, medicine, and psychology. Scope means the ideas are not limited to specific artificial circumstances that are created by the researchers. Milgram's experiments on obedience in America can be used to explain how people behave in militaries around the world. Then we have simplicity. This is captured by a phrase that I'm sure you have heard before in some context, Occam's razor. The idea that when multiple explanations are available, the simplest one is usually correct, and that is the one we should prefer. And finally, fruitfulness, that the ideas we come up with are useful to people with lots of different applications and in different industries, including lots of non-scientists, will pick up on them and use them to their advantage. If science is worth anything, then lots of people will use it. Now we have a set of ideas called Mertonian norms, named after the American sociologist Robert Merton. The first is communalism. This is the idea that all scientists should have common ownership of scientific goods, like intellectual property, in order to promote collaboration. Secrecy is the opposite of this norm. And we'll talk a whole lot more about openness, including the open science movement, in our discussion of the replication crisis. Then we have universalism. This is the idea that scientific validity is independent of the socio-political status or personal attributes of its participants, meaning anybody can do science. Science is something that anyone, regardless of demographics, can do, regardless of gender or race or religion or socioeconomic status. Anyone can be a scientist. Disinterestedness refers to the scientific institutions acting for the benefit of the common scientific enterprise rather than the personal gain of the individuals within them. In other words, we're working toward the broader goal of establishing knowledge rather than to benefit one's personal status. Then we have organized skepticism. This is, I think, one of the more underrated aspects of science, or the underappreciated aspects anyway. This is the idea that scientific claims should be exposed to critical scrutiny before being accepted, both in methodology and in institutional codes of conduct. What that means is that we should have a skeptical mindset when approaching any new ideas, even if we like them emotionally. Now we're going to switch gears here a little bit and talk about a concept called falsifiability. This is in your textbook, and I want to talk about it more here in the context of two people. One, Sigmund Freud, perhaps the most famous psychologist in history, and also another person named Karl Popper. I want to talk about the ideas that Freud proposed and how we know those ideas are not only false, but also unscientific, and then Karl Popper's contribution to philosophy of science. Freud should get credit for putting a lot of ideas on the table to investigate. Freud did have some good ideas. He coined terms like the subconscious, which sparked research on implicit or automatic mental processes, and he also suggested the importance of early experience for future developments. But he also had some really wacky ideas. He claimed that most human behaviors stem from sex drive. For example, Freud suggested that we build skyscrapers to reflect some kind of sexual impulse because buildings are like penises. And that's pretty wacky. And he also refused to acknowledge counter evidence for his ideas. According to Freud, anything could be used as evidence to support his theory, and that's really bad. I'm going to illustrate this with a fictional conversation between someone with their therapist. So imagine someone goes into a therapist's office, and he's talking about why he's distressed, and he says, "I feel guilty about my sexual urges." And the therapist explains, "Yeah, that's because of libidinal conflict with your mother." But then the person goes on to say, "I don't have enough time for my hobbies and my family." The therapist responds, "That's also because of libidinal conflict with your mother." And the person responds, "I'm also very concerned about nuclear war." Right. Also mom's fault, and also sexual. So you can see the problem here. The problem is that anything and everything would be considered supporting evidence for Freud's theory, which is preposterous. And by the way, when questioned, Freudian theorists would often respond just by saying, "Well, you don't understand the theory well enough, but just trust us, it's happening." And this is not a very good way of doing science. That's why Freud's ideas are not only incorrect, but also unfalsifiable. So this was the key insights that Popper had. Karl Popper suggested that a theory or hypothesis is falsifiable if it can be logically contradicted by an empirical test. So, for example, the claim that all swans are white is false, but it is falsifiable because the mere existence of black swans proves that it's wrong. So as soon as we find any black swans anywhere in the world, we can falsify this claim. There was no way to falsify Freud's claims, which is why they're unscientific. Another way of saying this, in the words of your textbook author, is we need to be able to articulate beforehand the kinds of evidence that will disprove our hypothesis and cause us to abandon it. So before we even come up with a serious idea, we need to be able to say, okay, if we observe X, then we know our idea is valid. But if we observe not X, we know our idea is invalid. And it's important to highlight what an important bit of progress this is. This is one of the ways in which we can demonstrate just how far science has come in the past century. We are in a much better place to do high quality research now than 100 years ago. And that's in large part thanks to our evolving notions of epistemology, our more advanced ways in which we can really know things. Now, in terms of interpreting research correctly, let's go back to our early example about online versus in-person learning. If you remember, I said that there really is no significant difference in terms of learning outcomes for people who are online versus in person. Well, how would we actually test that idea and establish its falsifiability, for example, with science? One way to do this would be to do a study where we put participants into one of two groups, on online learning, the experimental group, or in-person learning, the control group, and then measure all of them with some kind of standardized outcome like an exam or an essay or a research project or something like that. And from the outset, we can say that there might be one of three or maybe more different results, but at least one of them would support the hypothesis. For example, if we found that the in-person learners scored higher on the exam than the online learners, that would support the hypothesis. But it could be that the results contradict the hypothesis. Maybe we get the opposite results. Maybe the online learners score higher than the in-person learners. Or we could see no difference between the groups. In fact, that last option, the no difference conclusion, that's what we see the strongest evidence for in existing studies now on learning outcomes across modality. Now, one other thing we should say here is that even if we establish with lots of studies a pattern of results, that doesn't mean we've proven anything. And I say this because when we talk about what science can do for us, everything that we know in our discipline, in our field, is probabilistic. We have degrees of confidence. And if you remember, the goal of science in this case is to reduce uncertainty. But this is not something that can be completely eliminated ever. So if you ever hear someone say, oh, well, science has proven this or science has proven that, that's actually incorrect. Science has never proven anything. And it's important to say that because a lot of failures in mainstream media coverage of science often get this wrong. This is one of my continued frustrations with how mainstream media covers science. People in the media want to be in the business of selling ideas and knowledge that are 100% true. And that strategy is actually very useful when it comes to current events. For example, it is absolutely 100% true that Donald Trump was indicted on charges of mishandling classified documents. There's no doubt about that. But science doesn't work that way. We can't report science that way because we're not 100% sure of any of this, and our scientific knowledge is constantly evolving. This is why we need to keep trusting the process. We need to keep doing science with confidence, even if we don't have 100% proof.